Okay, let's try. How about derivative? What? Sorry, went crazy. Derivative of 5x squared plus 1 times x to the 4 over 3x squared plus 2. All right. This is one of those where you got to do the product rule and the quotient rule sort of at the same time. One way that you can make this simpler, so one strategy that some people like to do is you could, just before doing the derivative at all, do the multiplication on the top, which will relieve you of having to ever do the product rule. You could just distribute the x to the 4 on top first, and then do the quotient rule, and it'll be just a simple quotient rule. Or you can try to do the whole thing at once. That's what I'm going to do. Let's try and just do the whole thing at once. So the derivative of that, let's say this is f of x. The derivative will be f prime of x, and it's going to be the quotient rule. So on the test, you better know, you have to have these things memorized: the quotient rule, the product rule, the chain rule. The quotient rule is the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Don't worry for now about the fact that you're going to have to do something weird on the top with the product rule. You should just start writing the answer using the quotient rule. So I begin with the bottom, which is 3x squared plus 2. Oh, something weird is going on with my screen here, sorry. 3x squared plus 2. All right, that's the bottom, which is how the quotient rule begins. And then I go times the derivative of the top. And here, I have to do the product rule. It's going to be kind of a big thing, but this is the derivative of the top. And what's that going to be? It's going to be, the product rule is the first thing times the derivative of the second thing plus the second thing times the derivative of the first thing. So I go first thing, 5x squared plus 1, times derivative of the second thing, 4x cubed, plus the second thing, x to the 4, times derivative of the first thing, which would be 10x. All right? So that's, this much is the derivative of the top. And in there, I did the product rule. All right? This, we're not done yet. Remember, we are in the middle of doing the quotient rule. I have the quotient rule says the bottom times the derivative of the top. That's what I did so far. And then I go minus the top times derivative of the bottom. So the top is all of that stuff, 5x squared plus 1 times x to the 4. And then times the derivative of the bottom. Derivative of 3x squared plus 2 is 6x. All right, this is the numerator of the quotient rule, and then remember the quotient rule always is all of this over 3x squared plus 2 squared. And that's the answer, all right? As usual, you should not attempt to simplify this unless you have a real good reason to, which in a problem like this, you do not have a good reason to. I just said find the derivative. That's the derivative. You might want to simplify it if I said something like find where the derivative is equal to 0. Then you would have to set that equal to 0 and solve for x, which is a real pain. I wouldn't ask you to do that in a problem like this. All right. Anybody have any questions about that one that I just did? So this was my example from the section on product rule and quotient rule. Nope. Just a moment. All right, let's continue. So that was product rule and quotient rule. The next thing on the sheet is about the chain rule. You've noticed probably as we proceeded that we really do the chain rule all the time when we're doing exponential and logarithmic functions. But the first time around, at least when we learned the chain rule, it was just about some stuff inside of a power. So let's try one like that. The chain rule is something we do all the time in different contexts, but a typical sort of easy chain rule example would be something like 5x to the 8 minus, oh come on man, 3x to the 4, something like that. This is a very sort of basic standard chain rule. You take the derivative of the outside part, which in this case is that fourth power, with the same thing on the inside, and then separately you multiply by the derivative of the inside. So in this case it looks like 4, then the same business in here. Change the exponent to a 3. So that much is the derivative of the outside with the same inside. And then separately, I multiply times the derivative of the inside. Derivative of 5x to the 8 would be 40x to the 7 minus 3. All right, and that is the derivative of the inside. This is the chain rule. All right, that's a pretty standard, straightforward chain rule. Any thoughts about that one? Any questions about what I just did? Nope. All right, let's just keep going down the list then. So that was the chain rule. One of them on the paper says find f prime of 1 or something like that. Remember, that means you got to take the derivative first and then you plug in that number. So like for that one, it says find f prime of 1. You begin by finding f prime of x, the function of the derivative, and then plug in 1. Sometimes people try to plug the number in first and then take the derivative. This is always a bad idea because after you plug the number in, you end up with a number as the answer, like a constant. And you take the derivative, you'll get 0. So you got to take the derivative first and then plug the number in. Okay, episode 14 is next on the list. I wrote them kind of out of order. That's because this is really a review topic. Logs and exponentials. So first one says a bunch of things. Compute these by hand. Let's try one of those. How about find by hand the log base 3 of 81. All right. These are not difficult, and you basically do it all in your head. There isn't much to write down in terms of the steps, but you have to, you have to have the proper idea of what it is you're doing here. Log base 3 of 81 equals what? I'm trying to determine. What is this? The way to think about this is you write this instead as an exponent. So this here is written in the logarithmic form, but you could also write it in the form of some exponent of something. And the little 3 down here is the base of the logarithm, which is also the base of the exponent, meaning you write it as the bottom. Really what this question is asking is equivalently written this way: 3 to what power equals 81. So when you see log base 3 of 81 is what? What you should be thinking of is 3 to what power equals 81. And you just have to, I suppose, remember sort of how to translate from one form to the other. This goes here, and then this one goes here, right? Anyway, what is it? From this point, you just have to guess. What is the power of 3 which equals 81? Now, maybe you can just pull that out of nowhere, or if you're really desperate, you could try and just like write down what are the powers of 3. 3 to the 1 is 3, 3 to the 2 is 9, 3 to the 3 is 3 times 3 times 3, which is 27. 3 to the 4 is 3 times 3 times 3 times 3, that's 81. So this is 81. So log base 3 of 81 is 4, right? 4 is the exponent which is required to get 81 when you do 3 to some power. This is how you do logs in your head. They could get a little sort of slightly weirder, perhaps, or more interesting. Here's another one. What about log base 3 of 1 over 9? What is that? To get a fraction, so it's the same question. I'm asking 3 to what power equals 1/9. To get a fraction as the answer, it means you're going to have to use a negative exponent. And in fact, once I say that, I hope you can just sort of guess along with me that 3 to the minus 2 is 1/9. 3 to the minus 2 means 1 over 3 to the 2. So you get 1/9. Anyway, log base 3 of 1/9 is minus 2. All right. Like I said, this is almost entirely just pulling the answer out of nowhere or guessing the answer. If you had to produce, like, show your work somehow, I would write something like that over there. This is why the log base 3 of 1/9 is negative 2. It's because 3 to the negative 2 equals 1/9. Any questions about those? All right, so that's doing logs by hand. How about the other types of question from that section was something like solve for x in a formula which has x inside the exponent. Let's try one of those. Solve for x in something like 5 plus 8 to the x equals 12. How about that? The basic idea is you're going to take the natural log on both sides and then move the exponent into a coefficient. That's the purpose of using the log in a problem like this, is so that you can move the exponent into a coefficient. But first, you must isolate the exponential part. So your first job is to isolate the exponential part, which in this problem is 8 to the power x. How we isolate that, I want 8 to the power x on one side by itself. We should begin by subtracting the 5 to put it on the other side. So I get 8 to the x equals 7. All right? And now I can take the log on both sides for the purpose of moving the x into a coefficient. So I go ln 8 to the x equals ln of 7. You actually don't have to use the natural log. You can use whatever log you want, but I'm always going to do the natural log. It's just how I roll. X log 8 equals log 7, and now we can solve for x by dividing the ln 8. X equals log 7 over log 8, and that's how we do it. This is how you solve for x when it's inside the exponent. This can be a little trickier if the exponent had more stuff in it, if it was like x minus 1, or on the sheet I can see one that says 2x plus 1 inside the exponent. We can do one of those later on if you want to come back to this section. All right. Any questions about that one that I just did? Excellent. Let's try. So the next section there is derivatives of exponentials and logs. So let's try just a very simple one. How about derivative of, how about 3 to the x plus 3x plus x to the 3 plus log base 3 of x plus ln x. Do you know how to do each one of those? They're all different. They look kind of similar, but I mean some of them do at least. But they all involve slightly different formulas that you have to use. So what do we get for, there's nothing special. These are all added together, so I'm just going to go down the list and do each derivative. Derivative of 3 to the power x. For that, you need to remember your rule about derivatives of of an exponential function, which is not e to the x. Derivative of a to the x is a to the x ln a, right? So when I see 3 to the x, I use this formula directly with a being 3, and I get 3 to the x ln 3. I just plugged into this guy over here. I plugged in a equals 3. Okay, plus 3x. What's the derivative of 3x? Somebody shout it out. 3. Yeah, thank you. Instantly. Shouted it out. All right. And how about x cubed? What's the derivative of that? 3x. 3x squared. Yeah, great. Those ones I just threw in there just to mess with you. You don't need any of this newfangled stuff to do those ones. Those are old, old derivatives. Of course, you should still know how to do those. What about log base 3 of x? For that, you need to remember this formula. Derivative of log base a of x is 1 over x ln a. So when I see log base 3, I just plug into that formula directly with a equals 3. I get 1 over x ln 3. All right. And then finally, ln of x, the derivative of ln. So this is another formula that you need to know. It's simpler. It's just 1 over x. So this is just 1 over x. All right. So these are very simple derivatives of exponentials and logs. In this vein, I might as well just write it down since I wrote all of these other ones. The other formula that you should know is the derivative of e to the x. This is the easiest of all. It is just e to the x. So when you take the derivative of e to some power, you just get the same thing again. And then you always have to do the chain rule when you're using these rules. If you have things inside other than just x, if there's some other stuff in there, you always multiply times the derivative of the inside. But we'll get to that. Those were just very simple ones. Let's try one that's a little more interesting. I'm going to try and leave those formulas. Maybe I'll put them over here. Let's try derivative of, how about 8 to the 5x squared minus 7x. How about that? 8 to the power 5x squared minus 7x, the derivative. Now, it is 8 to some power, so I am basically going to use this formula here, because this is what you use when you have something to some power where the thing is not e, right? you use this one when the variable's in the exponent, but the base is not e. So it says when I have a to the power x, the answer is a to the power x again. That is the same thing again. So 8 to the 5x squared minus 7x. And then times ln, in this case, of 8. So I have plugged directly into this formula using a equals 8 and using x equals 5x squared minus 7x. All of that stuff is playing the role of x. All right, we're not done because we got to do the chain rule. As always, unless it's just x up there, if it's just x up there, you don't have to do any other chain rule stuff. But if there's anything else up inside the exponent, you have to do the chain rule. Multiply times the derivative of the inside of the exponent. In this case, it would be 10x minus 7. So, and that's it. That's it for this answer. That is the derivative of that business. All right. Let's try one more. Let's try one with a log in it. So how about log base 5 of e to the x plus x to the 5. All right. Again, this is going to involve a chain rule because I have some fancy stuff inside of the log, but the basic the first pass of this, I'm going to use this rule right here, derivative of log with some different base. This is a log with base 5, and so I'm going to use this over here using a equals 5, and x, playing the role of x, is all of that stuff, e to the x plus x to the 5. So I get, as my answer, 1 over x ln a, but instead of x, it's e to the x plus x to the 5. And then ln a would be ln 5, all right? You better have those parentheses in there. They matter because they indicate that you should add those things together before you multiply by the log of 5. Okay, this is the first pass. I just used the formula, and now I have to do the chain rule. Multiply this times the derivative of the inside. And make sure when you do these chain rules, you don't stick this in the denominator with all that other stuff. It multiplies just, it's this fraction separately times this other stuff. The other stuff is not part of the fraction. Anyway, what is the derivative of e to the x plus x to the 5? Derivative of e to the x is e to the x. Derivative of x to the 5 is 5x to the 4. And that's how we do it. Any questions about that one? These ones are a little tricky, but you did them last week on the homework and such. All right, next section is the last bit there, increasing and decreasing. Let's try this out. So these are the new ones for this week. First thing is you should be able to look at a picture and identify when the graph is increasing and decreasing. So let's see if I can draw an example of this. Something like that. I just heard my doorbell ring in real life. I think it's my kid. Maybe the door was locked. I think they're doing okay. All right. Where is it? Let's say give intervals where it's increasing and decreasing. All right. So you got to look at the picture here and decide where is it increasing and where is it decreasing. So increasing means it's going up as it goes to the right. That means this way, right? And decreasing means it's going down as it goes to the right. That means this way. So increasing would be like this blue section. All these values until there, they are increasing. And also these values here, they are increasing. And where is it decreasing would be in here. These are the ones where the values are going down as we go to the right. These are decreasing, all right? It's not hard to identify on a picture where it's increasing and decreasing. I said to tell me in terms of intervals, so I would say it's increasing on the interval minus infinity to this point here, which is 1. Remember, you are saying when you give me intervals, you are describing the x values. So all the x is less than 1. And then also from here and to the right, so this is 1, 2, 3. So I'm going to say 3 to infinity. All right? That's where it's increasing. Where is it decreasing? The red business is in the middle there from 1 to 3. Decreasing from 1 to 3. That's it. Oh. All right. Any questions about that? This is just doing it on the graph. This, if you know what to look for, this is not difficult. Where is it going up as you go to the right versus down as you go to the right? Okay, the more in-depth stuff comes when you're trying to do this same procedure but using equations. So let's try one like that. So let's find where it's increasing and decreasing. And for this, I'm going to look up an example in the book. These ones, if I just make it up at random, probably the numbers will be messy. So if you don't mind, I'm going to pick one from the book. And I'm going to try and pick one that's not also on the homework. Let me just look at the homework assignment. I don't want to spoil the homework. All right. Let's try, I'm going to do number 16 in section 5.1, in case you care. This is not on the homework. F of x equals 2/3 x cubed minus x squared minus 4x plus 2. All right, these problems actually will take you quite a bit of time to do. This one might take, 10 minutes to do one of these. On the test, I'm certainly not going to ask you to do more than one like this. Find where it's increasing and decreasing. So you begin, there's a bit of a procedure that you'll need to remember what to do, but you should start by taking the derivative and setting it equal to 0. So actually this is true for most of the problems that we're going to do, like for the next several weeks. If you don't know what to do, probably you should begin by taking the derivative and setting the derivative equal to 0. This turns out to be useful for answering all kinds of different questions. Anyway, the derivative, 2/3 x cubed, the 3 comes down and gives me 2x squared minus another 2x minus 4, and the plus 2 goes away. All right, that's the derivative. And now you should try and simplify this as much as possible with the expectation that you're going to set it equal to 0. So in order to simplify this, first I would factor a 2 out. There's no reason to keep that in there. X squared minus x minus 2. All right, and then I can actually factor that quadratic in there, 2, and then x minus 2, x plus 1. All right, this is f prime of x, remember? This is going to be important later on, so I'm going to sort of put that in a box so we can remember that. Actually, for the rest of the problem, the original function is not relevant anymore. This is all I care about from now on. Like I said, I'm going to take the derivative, I just did, and then set it equal to 0 and solve for x. Okay. 2 times x minus 2 times x plus 1 equals 0. Solve for x. First of all, the 2 can just divide away entirely. I divide both sides by 2. On the right, I get 0 divided by 2, which is still 0. So this is just x minus 2, x plus 1 equals 0. And then this is already factored, so I can just say x minus 2 equals 0, x plus 1 equals 0. I get x equal 2 or x equal minus 1. All right, these are what they call the critical numbers. These are numbers where the derivative equals 0. You also need to determine where the derivative does not exist. But in this case, so actually usually I put a little heading of what I'm doing. F prime equals 0, that's what I just did. You should also consider when f prime does not exist. But in this case, I'm going to put sort of a NA. In this problem, f prime always exists. You should be worried about when you could possibly get 0 in the denominator or something. That would cause a DNE kind of situation. But that doesn't happen in this example because there's no denominator. All right, so my critical numbers are these two guys. Critical numbers. All right. How we finish the job here, say when it's increasing or decreasing, is we're going to make a little chart involving the critical numbers. I'm going to label them on my chart in their appropriate, numerical order. These are the critical numbers. These are my x values. And then what about my f prime values? Well, at -1, the derivative is 0, and at 2, the derivative is 0. That's the reason why I found those points. I found them by verifying that the derivative equals 0 at those 2 points. And then, what about in between I want to know the signs of the derivative in between those points. And to do that, we choose our favorite values in between. So you need to choose some value over here, some value in here, some value in here. And it could be whatever you want, just your favorite number in each of those ranges. So to the left of -1, I'm going to choose -2. And you plug that number into the derivative, f prime of -2. What's it going to be? Use this formula up here, which I put in the box for the derivative. When I plug in, it's going to be 2 times -2 minus 2 times -2 plus 1. What is the sign of that? It doesn't actually matter what this is as a number. It matters what the sign is. But you can tell this is a positive, this is a negative, and this is a negative. And when I multiply them, positive times negative, this is positive. And so I'm going to put a big plus sign right there to indicate the derivative is positive. That means actually it is increasing right there. So that's going to be part of our answers. It's increasing on that interval. Okay, what about in the middle? My favorite number in between -1 and 2 is 0. Let's plug in f prime of 0. What did I... Sorry, I'm just now realizing I had a typo a few minutes ago. It's so embarrassing. I wrote f prime of 0 right here. I shouldn't have written f prime of 0. I meant f prime equals 0. This is where the derivative equals 0. Sorry, can I just write f prime? That's what this chart, this line of the chart here is indicating the values of f prime, be they positive, negative, or 0. Not the values per se, but the signs. Okay, anyway, f prime of 0. I plug into the box. I plug x equals 0. What do we have here? We have a positive here, a negative here, and a positive. And when I multiply positive times positive, I get negative as the answer. Right there. That line there is a big minus sign. And then finally, one more thing to plug. Oh, did someone have a question?
Yeah, I have a question.
Yes.
How do you know that, like, this is kind of dumb, but like you said 1 positive and 2 negatives is positive and 2 positive and 1 negative is negative. Can you explain that?
Yeah. So it's basically if you have an even number of negatives, it ends up being positive. If you have an odd number of negatives, it ends up being negative. Because every time you multiply by a negative, the sign switches. So if you have 2 negatives, the sign switches twice, which means it's positive again. Does that make sense?
Yeah, sorry.
I don't know who asked the question. Yeah, great. So in this case, I have only 1 negative, which means it's going to be negative. Which is why I put the big old minus in the middle. Okay, and then finally, last value to plug in. I'll do f prime of some value to the right of 2, which is my favorite number to the right of 2 would be 3. I always try to choose, the easiest number to plug in. I'm plugging into the formula in the box. X equals 3. 2 times 3 minus 2 times 3 plus 1. Here, these guys are all positive, and so the answer here is positive. I'll put a big old plus there. And now we are ready to say the final answer. The derivative being positive or negative tells you if it's increasing or decreasing. So I'm going to say the original function f is increasing on the interval. So it's increasing here and here, right? That would be minus infinity to minus 1 and 2 to infinity, right? Those are the intervals where it's increasing. And then decreasing, I'll do that in red. The one in the middle, right? Minus 1 to 2. That's how we do it. Any questions about that one? So these ones can be a bit harder if the function has like exponentials in it. That can happen sometimes. We could do an example like that if you want. Or, I made it through I did one from each section, which was my original goal. Now we can talk about whatever any of you wants. If you have specific questions or just, do another one like this, but harder. I wasn't trying to do the absolute hardest ones. You can do harder ones if you like. What do you think?
Can you do one like this, but when there's no critical numbers?
No critical numbers. Okay, yeah. That is, I think, was there one on the homework like that? Yeah, this is a weird case that ends up being actually easier. if there are no critical numbers at all. So here's an example where that happens. How about f of x equals 5x plus 3? We do the same procedure. Let's just see what happens. I take the derivative. It is 5, right? And then I try to set the derivative equal to 0. You know, I simplify the derivative, but that's as simple as that's going to get. Set it equal to 0. F prime equals 0. It looks like 5 equals 0, and this is not true, right? Which means your interpretation when you see something like that is just that this can never happen. This is impossible. And so what that means in the case of this problem is f prime is never 0. All right. We should also check when f prime does not exist, but just like before, there's no denominator or anything like that, so this is also not going to happen. So there are no critical numbers at all. That means when I write my chart, there just aren't any points to indicate on my chart. I'm not going to label any specific points. This is a weird example. What about the derivative, though? You can still verify. Remember, in the case when there is really a chart, like over here, you choose values in between the critical numbers. All right. The reason we choose values in between is because the zeros here determine when the signs switch from positive to negative. But in this example, apparently, the sign, whatever it is, it never switches from being positive to negative. And so I can just plug a single number in anywhere and determine if it's going to be positive or negative, right? So we can choose any number to get, remember our goal here is the sign of f prime, okay? But in fact, you don't even, in this example, it's so simple, you don't even need to plug a number in to say what the sign of f prime is. Can you say, like, what is the sign of f prime of x? This is f prime of x. It's already just a number, and it is a positive number. So the sign is positive. All right. If you like, you could have plugged, like I said, you could choose any number. So in particular, I could say, for example, f prime of 0. What is it? It's 5, because f prime of x equals 5. That means no matter what number you plug in, you're always going to get 5 as the derivative. Anyway, it's positive. And so the derivative is always positive. In terms of intervals, I would say f prime is positive always. So it's increasing. F is increasing always. If you insist on writing it as an interval, you can say it's increasing on the interval minus infinity to infinity. That is all real numbers. So when there are no critical numbers, this is a weird case, but it's not hard. It's actually easier. But you just have to know what to do in such a weird situation. Is that what you had in mind?
Yeah, I was just like confused, like number 24 on the homework. It was a quotient or fraction.
Okay, so number 24 actually does have critical numbers. They are when the denominator equals 0 in the derivative.
Oh wait, I meant 23. I'm sorry, that was my fault.
23. Okay, same thing. In such an example, so maybe I'll try one like that. This is not the same, but I'm going to make up 3x plus 1 over x minus 3. Can we try the same procedure here? I begin by taking the derivative. You have to use the quotient rule. So I go to the bottom. This one's kind of hard. I'm gonna try and do it fast just so hopefully we can get one more question in. The bottom times the derivative of the top, which is 3, minus the top, 1, times the derivative of the bottom, which is 1, all over the bottom squared. All right. And then in this case, usually I would leave my answer like that, but there's a much larger problem you have to do here. You got to simplify that in order to do the next step. So we better distribute on top the times 3. It's going to be 3x minus 9 minus 3x plus 1, I don't have to write times 1, that doesn't matter. Divided by, I'm going to leave the bottom like it is because it's not helpful actually to simplify that on the bottom. And then what do we got? Distribute the minus sign. 3x minus 9 minus 3x plus, no, minus 1. Distribute the minus sign, right? Over x minus 3 squared. Okay, and these 3's cancel. I get negative 10 on top. X minus 3 squared. All right, this is the derivative. It's not going to get any simpler than that. This one, if you set the derivative equal to 0, you will find no solutions from that. You also need to check when the derivative does not exist. And in this case, you do get answers. You set the denominator equal to 0. That square doesn't matter because you can square root on both sides. And so you do have a critical number, x equals 3, to put on your chart. And that'll get you going. I don't think we need to finish this one. All right. So the one on the homework, the fraction, you should still get a critical number. All right. What else? We got 10 more minutes. Anybody want to suggest one more to do or two more, depending on how hard it is?
How would you do the log and exponentials, like when it says solve for x in e of x if 2x plus 1?
Sure. Here, I'll make up another one like that. How about, this will be even harder. Can you imagine? It's not really harder. It's more or less the same. You should begin by taking the natural log on both sides. And so, natural log e to the 4x equals natural log 7 to the 1 minus 2x, like so. And then move the exponents down in front. That's the purpose of taking the natural log on both sides. So on the left I get 4x ln of e, and on the right I get 1 minus 2x, make sure to put the parentheses there, ln of 7. All right. There's one thing you can simplify here. ln of e, actually that's a thing that you should know. And can anybody shout out, what is ln of e? It is 1. Yeah, this is actually the purpose of the number e. The reason why e is so awesome is because the natural log of e is 1. Or another way of saying it, you can say that's what's special about the natural log, is it is the one for which the natural log of e is 1. So worth remembering, ln of e equals 1. Also worth remembering, ln of 1 equals 0. Although that's not relevant in this problem. So ln of e is 1. That means the left side is just 4x. And then 1 minus 2x ln of 7. All right, our job here is to solve for x. This is still a little tricky because x, it's not easy to isolate x here. Right now x is on both sides of the equation. It's not immediately clear how to get it all on one side. But the trick is on the right side I'm going to distribute ln of 7. Remember, the natural log of 7 is just a number. So we can, even though it looks a little weird on the paper, we can still imagine it as a number. So this number here, ln of 7, distributes onto the 1 and also onto the 2x. What do I get? 4x on the left. On the right, ln 7 minus 2 ln 7. Sorry, that's a weird looking 7 times x. All right? I multiplied both of those things by ln of 7. Okay? That x there is not inside the log. It's just the log of 7 and then separately times x. You could do that if you want to make it a little less ambiguous, although those parentheses aren't technically necessary. Okay, now can we isolate the x? I think now we can. I have the 4x here and the 2 log 7x. I want to put those both on one side of the equation. let's put the x's stuff all on the left. So I'm gonna add this over to that side I'm gonna move this over to that side by adding. So it's going to be 4x plus 2 log 7 times x equals ln 7 was on that side by itself. Getting there. What should I do next to solve for x? I need to get x all by itself on one side. Anybody remember?
Can you divide it?
Divide it, kind of. Would you mind if I say I'm going to factor it? Maybe that's what you meant. On the left side I have two things. Each of them has an x on it, which means I can pull the x out. And what remains from those two things is 4, the first one, and the second one, 2 ln 7 equals ln 7. And then here we can solve for x by dividing 4 plus 2 ln 7. So x equals log 7 over 4 plus 2 ln 7. There you go. Any questions about that? These ones are a little tricky. They involve some fancy algebra to finish it off. All right. What else? We got 5 minutes. We can do one more. Maybe you don't want to do one more. I don't know. How about just for fun, let's do one more derivative of some complicated something. Let's try derivative of log base 7 of x times root 2x plus 1. I'll try and do a complicated one here. It's a complicated one. I don't know if it looks complicated. One thing you should always do, at least in your mind, you don't have to write this as a step unless you want to, use a 1/2 power in place of the square root. That's always preferable in this class. So this is the same. I'm not doing the derivative yet. I'm just rewriting like so. All right. What can we do? What's a fella to do for the derivative of this? Well, it is a log base 7 overall, so I'm going to begin by using my rule for the derivative of a log base a. Remember, it's 1 over x ln a. And so that's what we're going to do first. 1 over. Now, in place of x, I have all of that business inside the big parentheses. It is x times 2x plus 1 to the 1/2. And then, in place of a, I have 7, so I put ln 7. So far, I have just written the result of this formula right here. That's not the whole answer, though. You always, when you use these formulas, you always need to do the chain rule if you have more complicated stuff on the inside. So next, I am going to do times, not inside the fraction, but just over here, the derivative of the inside, that is to say that stuff. What's the derivative of that stuff? And how am I going to do that derivative? I got to use the product rule, don't I? This stuff on the inside is a product, right? There's multiplication right there, x times that other thing. So inside my big parentheses here, I'm going to do the product rule with those two things. The product rule, remember, is the first part times the derivative of the second part plus the second part times the derivative of the first part. Let's do it. The first part is x times derivative of the second part. How do I do the derivative of the second part? That would be this thing here. For that, actually, we got to do the chain rule. Can you believe it? The chain rule with that thing, because I have some stuff with an exponent. So it's going to be 1/2. Same thing on the inside, change the exponent, times the derivative of the very inside of that is 2. All right. So all of that is doing the chain rule to get the derivative of the second part of the product rule inside there. And then, continuing the product rule, I go plus the second part like it is, 2x plus 1 to the 1/2, times derivative of the first part, derivative of x is 1. And that, my friends, is the whole answer. Of course, don't try to simplify that. All right, and I think, any questions about that one? That one's kind of a hard one. That's what my daughter says. We went to like a Chipotle. It was the Qdoba. It was like Chipotle. She was like 6 years old. She walks right up to the counter and says, "I want a hard one," meaning she wanted a taco with the hard shell. But, I thought that was funny. That was a hard one. All right. I assume you all thought it was funny too. I can't see or hear any of you. Any last minute questions? I hope you're feeling good about all this. I do, I'm going to say goodbye to you right now, but I have office hours like now immediately. So if you do have more questions, feel free to hang around. I'm going to go make my lunch, but I'll be back in 10 minutes or so, and I'll be ready for more. All right?